Hello everyone, and welcome to the video that I have for section 7.3, where we look at the polar form or trigonometric form of a complex number. The skill objectives for this particular video are number 1, graph a point in the complex plane. Number 2, convert complex numbers from rectangular to polar form. And number 3, convert complex numbers from polar to rectangular form. Conceptual objectives for this one are first to understand that complex numbers can be represented in rectangular or polar form. Number 2, relate the horizontal axis in the complex plane to the real component of a complex number. And number 3, relate the vertical axis in the complex plane to the imaginary component of a complex number. The first thing I'd like to do with this is to recall some things with complex numbers. The one thing you want to remember is a complex number is a number z. We often use z to represent a complex number. And that z will be equal to a plus bi, where a and b are real numbers. So you'll recall that definition from earlier in this year and from last year when you were in Algebra 2. One of the things that we have, that a value is called the real component of z, of the complex number, and the b value is called the imaginary component of z. So if I take a number, complex number, something like, let's say 4 minus 3i, then 4 would be the real component and negative 3 would be the imaginary component, because I would think of that as plus a negative 3i. Okay, so that's one of the things you have to keep in mind with these. So let's go on to the complex plane. When we look at the complex plane, one of the things that people did over time, there was a long time where people were coming up trying to, once they realized complex numbers existed, then it became a matter of interpreting them geometrically. How do we go through and get a visualization of a complex number? And eventually somebody came up with the idea of the complex plane. In the complex plane, what we have is the horizontal axis represents the real axis. So that's would also be the real component. The vertical axis is the imaginary axis. So that would be the value of the imaginary component. So when I look at a complex number in the form of z equals a plus bi, what you'll see on that is that we will go, the real component is a, so I'll locate where a is. We'll just say it's right there. The imaginary component is b, not bi, it's b. The imaginary component is b, so we'll say, well, there's b. And so we go to the point AB, and that right there represents the complex number z equals a plus bi. Now, one other thing that they will do with this, because of how these things, how we end up plotting these, that we have our horizontal axis and our vertical axis. One of the things that they will do is that instead of z equal a plus bi, you'll also see that as z equals x plus yi. Okay, so in fact, in the book, they're going to use this version a lot in terms of as we move forward and going between polar and rectangular and polar. Now let's take a look. I want to do some examples here in terms of plotting the complex number. So the first one we're going to want to plot is going to be z1, which is 2 plus 3i. And so in that case, I look at this. I know my real component is 2. My imaginary component is 3. And so what I'm going to do to plot z, I'm going to go to the point 2 and then up 1, 2, 3. So I'd be at that point, and I'm going to put a dot there. And then that one is just going to be, I'll label that as z1. Okay. Let's take a look at at z3 for a second. Z3 is 6. Now you got to keep in mind that would be 6 plus 0i as well. But typically when we look at those, you're just going to see that 6. And so what we're going to do in terms of plotting that one, it's the real component is 6. The imaginary component is 0. So it's just going to go out to 6 on that real axis. So 1, 2, 3, 4, 5, 6. And so I will put a dot there. And that is Z3. What I'd like you to do right now is I'd like you to pause the video and I want you to plot the remaining complex numbers. So I want you to plot Z2, Z4, Z5, and Z6. So pause the video, plot those, and then come back. We'll take a look at how you did. Welcome back. In this case, the first one that we wanted to do was Z2, which is -4 plus 7i. So I would go over -4, 4 units to the left, up 7, and Z2 is there in red. We'd already done Z3 and Z1, so Z4 would be the next one, which is 2 minus 5i. So that's 2 on the real. The real component is 2, -5 for the imaginary component, and that gets us here. Now, Z5, that is -4i, which would be 0 minus 4i. I could think of it that way, which then that means it's going to be right on the imaginary axis at -4. So we're right there at the Z5. And Z6, the real component is -5. The imaginary component is -2. So Z6 would be right there. So double check, make sure you have those. Be careful. I think probably the ones that could cause the most problem, I think, is something like Z5 or Z6 or Z3, where you're looking at only one component. It's very easy to make that mistake. So just make sure that that component there for Z5, you did go down, you didn't go across, because that could be a problem there. Now what we're going to be looking at as well is going to be what's called the modulus of a complex number. Modulus is a fancy word for saying the absolute value of a complex number, and therefore it is the distance from 0. And 0 in the complex plane is the origin. So what you're really looking at when you're working on these things is going to be finding the distance from the origin to the point that you've located for that complex number if you were to graph it out. So again, what you want to do with this is keep in mind that z is a plus bi, or we're gonna write it now as x plus yi. And just kind of recall quickly that if I had a vector z, x, y, then the magnitude or modulus of z would be equal to the square root of x squared plus y squared. And that's really what's going to end up happening with this as well. And so we have that the modulus or magnitude of a complex number, z equals x plus yi, is the distance from the origin to the point xy in the complex plane. In other words, the absolute value of z is equal to the square root of x squared plus y squared. Now, an alternate form of this is the idea that you remember that every complex number has a conjugate. The conjugate of x plus yi is x minus yi. Well, if you take the product of a complex number and its conjugate, it will always end up equaling. That product is going to end up being equal to that if you go through and do that one. So you'll see that's another form of that. Remember that the little bar above it for our textbook is the complement of that complex number. Let's take a look at a couple examples here. In this case, what we want to do is we want to find the modulus, or the absolute value, if you will, of the complex number. So in this case, I want to remember that it is always equal to the square root of x squared plus the y squared. So for z1, if I want the absolute value of z1, that's going to be the square root of 2 squared plus the -3 squared. Notice the I is not coming along. You got to remember, I is not part of it. It's what we use to determine which one is x and which one is y, but it's not actually part of y. So that will be the square root of 4 plus 9, which is the square root of 13. What I'd like you to do right now, I would like you to pause the video, and I would like you to go and identify the modulus, the absolute value, of each of the remaining 3 complex numbers. So pause that video, see what you come up with, and when you get back, we'll take a look at how you did. Welcome back. So in this case, I've gone through and done set each one up. What you have to remember on here for Z2, Z2 right now is 4, but we can remember that as 4 plus 0i. And so in that case, the modulus of Z2, or the absolute value of Z2, is the square root of 4 squared plus 0 squared, which is the square root of 16, which equals 4. The modulus for Z3 is going to be the square root of negative 12 squared plus negative 5 squared. Well, negative 12 squared is 144, negative 5 squared is 25, and that's the square root of 169, which equals 13. And the last one, the modulus for Z4, you should have, when you set it up, you should have had the square root of 4 squared plus 2 squared, which would be square root of 16 plus 4, which is the square root of 20. And the square root of 20, which is 4 times 5, does simplify to be 2 times the square root of 5. So there you go. Double check your work. If you have any questions, make sure you write them down. Otherwise, if you're feeling okay with that, then we will move on. Now let's take a look at the trig form, or the complex numbers in polar form. Now, what we want to do is I want to go back in time for a second. I want you to recall from section 4.3, which is where we looked at we were told that the terminal side of an angle theta went through a specific point x and y. And from that, we knew that the sine of theta was y over r, the y coordinate over r. The cosine of theta was the x coordinate over r. And the tangent of theta came out to be y over x. And again, where x does not equal 0. The other thing you had with this is r was equal to the square root of x squared plus y squared. So that probably is starting to look familiar to you again. Well, what happens here, if we take these two and we solve them for x and y, what we get is that x equals r cosine theta and y equals r sine theta. So what I know right now, I have a complex number, and that complex number is z, and that's equal to x plus y times I. And what I'm going to do is I'm going to replace x with r cosine theta and y with r sine theta, which gives me r cosine theta plus r sine theta times I. Again, all I've done at this point is I've replaced the x with r cosine theta and the y with r sine theta. And the last thing we do is we can pull out the common factor of r. So that equals r times the cosine of theta plus I'm going to move that I out in front, so it'll be I times the sine of theta. Remember, it's sine of theta and I, it's multiplication, so I can do it in any order. And just to make it a little bit easier to work with, we will have it in that form. And that right there is what's called the polar form, or the trigonometric form of a complex number. So what we have now is that the polar form of a complex number, that z equals r times the cosine of theta plus I sine theta. That's that polar form of a complex number. R represents the modulus of the complex number, and theta represents the argument of that complex number z. So what you're going to see is that r is also called the mod z, and theta is the arg z, or argument of z. We'll just say argument of z. But the other thing you want to keep in mind here, and this is going to have ramifications later on, that theta must be between 0 and 2 pi, or 0 and 360 degrees. So we're looking at something that is a positive angle measure for every one of these. We're looking at a positive angle measure in that first rotation, first time around what would be the unit circle. So one of the things we're going to be asked to do is convert a complex number from that rectangular form, the x plus yi form, to the polar form, the r times the quantity cosine theta plus I sine theta form. And so what we want to do, the process is this. The first thing you're going to want to do is plot that complex number in the complex plane. And the reason you want to do that is for this piece right here. You want it to be able to identify which quadrant you're working in. The second step you need to do is you need to find r. And you know r equals the square root of x squared plus y squared, or you want to find the modulus of that complex number. The next thing you want to do is find the argument of the complex number, which is theta. And you're going to use this fact here that tangent of theta is y over x when x does not equal 0. But again, you got to keep in mind that theta must be in the quadrant identified in step 1, which that does cause us problems. Okay, we got a couple issues. Number one, in order to solve this, if this is not a tangent value we recognize, then we use the calculator. The calculator, if this is positive, is going to give us an angle in quadrant 1. If it's negative, it's going to give us a negative angle in quadrant 4. And so in order to do this, remember theta is going to be something from 0 to 2 pi or 0 to 360 degrees. So what I'm going to have to do is if I go through and remember what quadrant I had in step 1, I'm going to have to go through. If it's in 2 or 3, I know I'm going to add pi or 180 degrees. So if we're in quadrant 2 or 3, we will add pi or 180 degrees. And if that angle was in quadrant 4, we know what we're going to get is a negative angle measure, but we want a positive, so we're going to add 360 degrees or 2 pi, depending on what they want. And then the last thing, once we've identified what the argument is, what the modulus of the complex number is and the argument, then we can then write that in its polar form. Let's take a look at a problem. In this case, what we have is z equals negative square root of 3 plus I. So the first thing I want to do on that is I want to plot that one out. So I plot it out, make just a little graph, and I'm going to say, okay, there's negative square root 3. That's my real component. And I'm at a positive 1i, so 1 there. So that there is my angle. And now I'm in quadrant 2 on that one. Okay. Next thing I want to find is the modulus. Modulus of z equals the square root of negative square root 3 squared plus 1 squared, which is going to be the square root of 3 plus 1, which is square root of 4, which is going to be 2. Next thing I want is to work with the argument of z. Argument of z, in this case, is going to be when the tangent, we know the tangent of theta is going to equal negative square root 3, or sorry, 1 over negative square root 3, y over the x. And I look at that one and I remember on there that that one happens at one of the angles on the unit circle. It can also be negative square root 3 over 3. But that one is going to happen when theta equals, we'll go with degrees, it's going to be when theta is 150 degrees. So you can check that out there. And so I want to write my complex number in polar form. So I know z is going to be equal to the modulus r, which is 2 times the cosine of 150 degrees plus I times the sine of 150 degrees. And that is the polar form of negative square root 3 plus I. The next one is 4 negative 3i. Okay, so on that one right here, I want to plot that one out. So I'll make my axes. And it's 4. Real component is 4. Imaginary component is a negative 3. So I get there. And that is my complex number z equals 4 minus 3i. I now want to go and calculate the modulus of z, which is going to be then the square root of 4 squared plus negative 3 squared, which equals the square root of 16 plus 9, which is the square root of 25, which is 5. So the modulus in this case of z is 5. The next thing I want to do is find the argument of z. Well, to find that argument of z, which we know is theta, I'm going to use the fact that the tangent of theta, in this case, is going to be negative 3 over 4. Well, I take that into the calculator, and we'll have it in degree mode, and I'm going to do the inverse tangent of negative 3/4. And when I do that, I come up with theta. So I know theta equals the inverse tangent, or arctan, of negative 3/4, and that comes out to be about equal to negative 36.87 degrees. But remember, our value in this case for theta, we're in quadrant 4, and because it's a negative here, and we're in quadrant 4, to go through and get the angle that we want, what we want to use for the argument here is we're going to add 360 to that. So I know the argument of z is going to be equal to the negative 36.87 degrees plus 360 degrees. And when I do that, that gives me 323.13 degrees. And so for this one right here, for 4 minus 3i, I know that complex number z is equal to my modulus, 5, times the cosine of 323.13 degrees plus I times the sine of 323.13 degrees. And that would be the polar form of that complex number. Pause the video right now, take a look at what I did to calculate each of those. And if you're feeling comfortable with it, then go on. Otherwise, make sure to note any questions you have, and we can go over those in class. The last thing we want to do is to convert from a polar form to a rectangular form. And so what I want to keep in mind here is that we know that x is equal to r times the cosine of theta, and y is equal to r times the sine of theta. So in this case, I know that for the first one, I know x is going to equal 5 times the cosine of 120 degrees, and I know y will equal 5 times the sine of 120 degrees. The cosine of 120 degrees happens to be negative 1/2, so x is going to be negative 5 over 2. And the sine of 120 happens to be square root 3 over 2, so y is going to be 5 times the square root 3 over 2, which is going to be 5 square roots of 3 over 2. And so I can actually write this one out. I could say, in this case, z is equal to negative 5 over 2 plus 5 square root 3 over 2 times I. So that would be, I've converted that one from polar form to rectangular form. The next one, I'm dealing with an angle that's not on the unit circle. So I have to go through again on that. I know that x is going to equal 4 times the cosine of 32 degrees. And so we just put that into the calculator. And when I do that, I get that comes out to be where x is about equal to 3.392. And then y is going to be 4 times the sine of 32 degrees. And I go through, put that in the calculator, and I get that y is about equal to 2.120. And so the rectangular form of this one, I would say z is about equal to, in this case, 3.392 plus 2.120 times I. So that would be the rectangular form of the complex number that we have right there. So With that, this now concludes the video for Chapter 7, Section 3 on the polar form of complex numbers. Make sure, again, to note any questions that you have, and be sure to ask them in class, and we'll see you in our next class.